So this is the fifth session in the subject of digital communications, and we are going to study formatting and baseband modulation in this lecture. So let us start. As we said, we are going to talk about two terms, formatting and modulation. Now, formatting is a term which has different meanings in different contexts, but in our context, what we are saying is formatting is a process in which a given signal is converted into a sequence of binary digits. As far as we are concerned, that is how we are defining formatting. What about modulation? Modulation is a process of converting the sequence of binary digits into a sequence of electrical waveforms. So that is what we mean by modulation. Understand that in general, modulation is often associated with carrier modulation, that is, sine wave is used as a carrier. However, we are talking about baseband systems here, and we are not necessarily talking about the carrier modulation. All right, so let us look at some of the details. Let's first repeat. Formatting refers to conversion of input signal into a sequence of binary digits. That is what we have already said. Now, the nature of this conversion will depend on the kind of signal that you have got. For example, if you have an analog signal, then the processing that you have to do before you get the sequence of binary digits is sampling, quantization, and encoding. These three processes are required. In our later lecture, we will study more details about these three processes. But the point is, if you have an analog signal, then you have to go through the process of analog to digital conversion, which consists of these three processes. On the other hand, you may have textual data that you want to send. For example, when you press a key on your keyboard, some binary code has to be generated. Which code depends on the system. For example, so this coding we call as encoding, and you could use ASCII code. That is one possibility. Okay, then let us look at the term modulation. We have already said that, but let's repeat. Modulation refers to conversion of binary digit sequence into waveforms suitable for transmission on the chosen medium. So, for example, you may have two wire lines, or you can have cables on which the baseband signal is getting transmitted. All right. So that these are the basic concepts for formatting and modulation. Let us now study the block diagram of the baseband system, and then we'll take the study further. So if you look at this block diagram, if you start with analog information, analog signal, then of course you have to go through the three processes: sample, quantize, and encode before you get your binary sequence. But if you start with the textual information, then these first two steps are not required. You directly go to encode. Of course, the nature of encoding will be different for analog signal and different for textual information. However, this is just a general block which says encode, even though the encoding will be different for analog and textual information. Then these binary sequence of digits is converted into electrical waveforms we call as the pulse modulation. Now you may have a source, a digital source, which is directly generating a binary sequence. Then these steps are not required. That directly goes to the modulation. Then before transmitting, so this block called transmitter may involve some kind of filtering or amplification, etc. Then it goes through the channel, which could be a two-wire line, or it could be a cable, coaxial cable, and so on. Then this receive block means that you do some processing of the received signal, maybe filtering, amplification, etc. And then since you had done modulation at the baseband transmitter, you must do demodulation. So the output of the demodulation at this stage will give you digital information, because remember, digital information was directly injected into the pulse modulation. So this can be recovered at the output of the demodulator. However, if either textual information or analog information was sent, then you will have to do the processing further. So this will go to decoding. Just as you did encoding here, you have to do the reverse operation. You do decode, and if it was a textual information, it is available at this point. But if it was an analog signal, then this goes through one more processing block called as the low pass filter, and you get your analog information or the analog signal. So this gives you an overall view of the baseband system, transmission and the reception. A simple block diagram. Now, next what we are going to do is to study the relationship between the data rates in bits per second and symbols per second. So let us start that study. So first let's assume binary modulation. Binary modulation means a 0 will be coded by one waveform and logical 1 will be coded by another waveform. So each binary digit is separately coded. So only two waveforms are required. So in this case, logical 0 is coded by one waveform. Let us call it as S1T. And let's say logical 1 is coded by another waveform and it is called as S2T. So to see this modulation, let's take an example. Suppose we have a sequence of binary digits which may be coming from the output of the encoder, or it could be coming directly from some digital information source. And suppose this is a sequence of binary digits, so 1 1 0 1 0 0 1. Then in modulation, what you do is 1 represented by S2T. So your first waveform will be S2T. Second again S2T because this is 1. Third is the digit 0. So you will now have the waveform which is S1T and so on. So understand that when you do binary modulation, only two waveforms are required. One represents logical 0 and the other represents logical 1. However, you can increase the efficiency of the system. Later on we will study the term efficiency, etc. But right now just note that if you do memory modulation, you can improve the system somewhat. So let us first of all define what we mean by this memory modulation. So instead of coding a single digital bit, what you can do is you can first acquire a group of bits, and this group is coded by a waveform. So for example, suppose as a sequence of digits keep coming, what you do is first you store 2 bits. So these 2 bits could be any of these combinations. So you may, the first 2 digits that you receive may be 0 0, could be 0 1 1 0 or 1 1, nothing else is possible. Next you again acquire a group of 2 bits, again it has to be one of these 4. And what you now do is, so these we call as symbols. So one symbol corresponds to 2 bits in this particular case. And then what you do is you code each symbol by a corresponding waveform. So SOT codes 0 followed by 0. S1T corresponds to 0 1. And S2T corresponds to 1 0 and S3T corresponds to 1 1. So you can see that the number of waveforms which are required is equal to the number of symbols that you have. And of course the number of symbols that you have will depend on how many bits you group. So in general, suppose the number of bits in the group is equal to k. See, in this case we have said 2 bits, but you can collect 3 bits, 4 bits and so on. In that case, the number of symbols and the number of waveforms will be 2 raised to k. For example, if k is equal to 3, then the number of possible combinations are 8 and you will require 8 waveforms. So of course the number of waveforms will be equal to the number of symbols, 2 raised to k, which we call as m, and that is why it is called as a emery modulation. So let's see one example of this emery modulation with m equal to 8. So suppose we are encoding characters. Let's take the word think. So this is a sequence of characters THINK. And suppose we are coding each letter by a 6-bit ASCII code. Then this is the code for T, this is the code for H and so on. So each of the letter is represented by 6 digits. So that is encoding, ASCII encoding, 6-bit ASCII encoding. But now when you group them, you can group them in various ways, maybe k equal to 2, k equal to 3 and so on. In this particular example, we are assuming that k is equal to 3. In that case, you will have 8 possible waveform, and of course one waveform for each group. So 001 can be coded as S1T, 010 can be coded as S2T, 000 is coded or modulated as S0T, and so on. So this is the sequence of binary digits, and this is the sequence of waveforms you have got. Remember, when you do binary modulation, you require only two waveforms. But when you do emery modulation, you require number of waveforms which is equal to m. In this case, it is equal to 8. Okay. Then, uh, just for your reference, I am giving a ASCII table here, and you can pause the video at this point, and whenever you need to use it, you can use it. All right. So this is just for your reference. Now, one last point before we finish this lecture is about data rates. What is the data rate in bits per second? How it is related to symbol rate, symbols per second, etc. That's what we want to study. All right. So let us first consider the analog signal. And let's say the sampling rate is fs samples per second. And so the time between samples, of course, is the reciprocal of this. So Ts will be equal to 1 by Fs. Now suppose there are n bits per sample. In that case, the data range in bits per second will be equal to n into Fs, because Fs is the sampling rate in samples per second. And for each sample you have n bits. So it is clear that the data rate in bits per second, BPS, will be n times Fs. What about the symbol rate? So it depends on how many digits you acquire. What is the value of k? So system waits to collect k bits to form the symbol. Then only you can output the symbol. Therefore, the symbol rate in symbols per second will be clearly bits per second divided by k, because you have to wait to collect k bits to form the symbol. So understand, of course, when it's a binary modulation, then k is equal to 1. So there is no difference between symbols per second and bits per second. But for emery signaling, clearly symbols per second is lesser than bits per second by so it's equal to BPS divided by k. Now this we have explained for the analog signal, but exactly parallel explanations can be given for textual information and the digital information. So let's quickly go through that. The only difference now would be that data rate, instead of being samples per second, it is characters per second. So let us say it is FCH. So again, the time between the two characters, TCH, will be reciprocal of this data rate in characters per second. And then you have, if you assume that you have n bits per character, how many bits depends on the kind of encoding you are doing. So in this case, clearly the data rate in bits per second will be n multiplied by FCH. And again, just as in the case of analog signal, the symbol rate will be the bits per second divided by A. That will be your symbol rate. Okay. Finally, if you consider the digital information, then the digital information is directly available. So you got data rates in bits per second, and again system waits to collect k bits to form symbol. So the symbol rate will be equal to bits per second divided by k. So in this particular lecture, we have given the definitions for formatting and modulations, and we also talked about the information rate in bits per second and also in symbols per second, and what is the relationship between the two. And that's all in this lecture.